So, so far we have studied some of the search algorithms where we have a goal and we are trying to find it by any algorithm. We start from certain initial state and go further. Last week we studied an algorithm which was uniform cost search. So if you remember breadth first search, so we say that each time we look for queuing function, mean how we're going to queue something in the open list or frontier. So for breadth first search, we say that first in, last out, last in, first out for the other one. For uniform cost search, the only criteria was to look for the cost of the path, and whichever path is giving you less cost, move to that path and so on. So that's why the queuing function for the case of uniform cost was sort by cost so far. So whichever node we are moving, we calculated, we did an example where we calculated at each node, we tried to calculate its distance from the, our path cost from the starting point, and this is how we move towards the end. And we said that the path we're going to find, the goal we're going to find would be least cost goal. Why? At each point we are choosing the path which is least cost path, and that means that it will lead to the final point. So this was about uniform cost search. We already did example, it's just a recap. Here we say that we want to go from Cebu to Bucharest. So how are we going to move? We're going to look for the next two nodes. So here you can see that from Cebu to Făgăraș, the distance is 99, here the distance is 80. So according to uniform cost search, the very first node that I'm going to choose, I'm going to move towards this point because the cost is 80. The next step would be to explore the next node. Now there are two possibilities for next node. Either I can go here or I can go here. But how I'm going to decide? I'm going to decide based on the cost. So at this point the cost was 80. If I'm not moving at the moment. If I move to this point, the cost would be 80 plus 97. But at each node, you look for all the nodes and try to look for the cost. So from this node, these two were the options. So I move towards lower cost, which is 80. At Ramenika, you had two options, to move to this point or this point. Here, the cost is 100 something, but moving here, cost is 99. So it means that it was better option to move to Făgăraș. Now, when we came at this point, what are two options? Again, the two options are, we can move to this or we can move to Bucharest. But from this point, we came to know that if we try to move to Bucharest, the cost would be 99 plus 211. It means that moving to this point was better option. So we will not move to Bucharest from here and we come to this point. And again, at this point, we look for the nodes. Which are the nodes? So we already explored this node. So it means that the next option is that I go to Bucharest from here. And if I calculate the distance, it will be 101. So overall, we can see that the adding a second path resulted 278, so previous path will be discarded and node will expand to the next point. So it means that here we were getting 310, here we are getting something like 278. So it means that the overall path, finally the search algorithm will explore all the paths, but then finally give you the path which is least cost path. So finally it will tell you that you should follow this one. So it was a uniform cost search problem. But even this problem, although it is somehow intelligent, informed search. In case of breadth first search, we were just keep on moving down one side or down on the other side. This is somehow informed search, but this is not categorized into informed search. So today what we're going to do, we're going to study informed search. As we know that uninformed search was, we termed it as blind search, that there is no problem specific knowledge. So we don't have any knowledge, we are just expanding the nodes. But in case of informed search, we will see that we will be having certain specific knowledge. We will be having some criteria to move on. We will be using some assessment methods to move further. In case of informed search, we have greedy based first search, we have hill climbing and so on. We will not be covering all of them, but these are some categories. So before we move to informed search, there are some new terminology that we're going to study. Some of them I will explain them now, but some of them time to time you will come to know that what each new terminology means. So as I said that in case of informed search, we're going to use some criteria. We're going to use some method to see if whether I should move from node A to B or node A to C. From a certain initial condition, which node would be better to move. So in order to do that, we're going to choose heuristics. What are heuristics? A simple definition is enabling someone to discover. It means that heuristic would be any function or certain thing. We will see now what it is, but heuristic can be something which could enable you to discover in a right direction. So heuristic, then optimal solution. We already discussed about optimal solution, a solution which can satisfy your constraints, which can satisfy your heuristic, can be an optimal solution, or any function that you want to satisfy would be your optimal solution. If, for example, you are saying that I want to reach to a final point with lower distance, so if there are two paths reaching to the final point, you will choose the optimal path which has lower distance. So it means that there is a certain criteria for choosing the optimality. We'll see later on what is admissibility and other factors. So let's introduce some new factors. G of n, you all already know. What is G of n? G of n is the path cost between any two nodes. Path cost. And we usually represent it by G of n. Not between, This is not between, actually not between two nodes. Path cost basically calculated at, whatever nodes you are at, you're going to calculate it from the initial state. So here the path cost was 99. At this node, the path cost was 211 and plus 99. So it means that G of n would be the true path cost. It means that whatever it could take actually. If I say, I could have said, okay, this could be one way to move forward, right? From Cebu to Bucharest, which is a straight line. But technically it is not possible, right? So it means that this can be a criteria, but this is not a very good criteria. So the true cost would be this way, which is the actual way if there are roads and so on. But what we can do, we will see later on, for the sake of algorithm, not to have the actual value. If, for example, I simply take straight line distance. So this is a straight line, this is a straight line, this is a straight line, this is a straight line. So this would not be a path cost, but this can give us a rough idea that how far we are from the distance, from the final location, a rough idea. This can be calculated by a number of ways. So the first thing that I told you, G of n, this is path cost, and this would be true cost of the path to reach to certain location. However, the other thing that I told you can be a heuristic. What does a heuristic mean? That it means we're going to see, we already use path cost, so for the moment we will forget about path cost, because we are moving towards heuristic, some more added benefits to our system. And later on we will see that we're going to combine cost and plus other things. So if, for example, I have somehow a straight line or rough estimate of the distance, so I can say, okay, if, for example, so if I write something with, if for example I say this is 310, or I can say if this is 320. So roughly I can say that the straight line distance was, no, it cannot be 2, the straight line distance was 290. So this is a rough estimate. Then I say straight line distance here was 99, let's say I'm taking example. So based on this, what I can do, I can see that where I am at the moment. So it means that heuristic will always give you information from the initial state to the goal. So it means that whatever heuristic we're going to define, it will always be a distance between the initial and the, so not the initial, between any state and the final state. Whereas the path cost was from initial to any node, but heuristic is giving you information from any node to the goal node. So, and heuristic can be a rough estimated cost, but it can give us certain information, a rough information. So, that's why we say that G of n path cost from initial state to state n, any state, like we have done in uniform cost search. H of n is heuristic. Heuristic means any function. Estimated cost, distance of shortest path from state to the closest goal. It means that heuristic is something which is telling us to take any node and use the shorter path to reach to the goal. Maybe it is not possible, we are saying, but for the sake of algorithm, we somehow calculate it. Similarly, take another node and calculate the shortest path. So this is the difference between a heuristic and a path cost. And we're going to use heuristic in the next application. So, as I said, heuristic. So, what are examples for heuristic? What are the example of heuristic? So, if I want to move from point A to point B, so heuristic can be a straight line. If I am driving a car or if I am walking, so heuristic can be a straight line. But if, for example, you are doing a puzzle, so if these are boxes of puzzles, so I have two options. If I go here, and reach here, or I have this option. So this is another example of heuristic. But heuristic would always be the shortest path, no other path. So if, for example, if I have two paths, one leading to the solution, I will take shorter path as a heuristic. So this straight line distance is called Euclidean distance, and the movements we take in puzzle is called Manhattan distance. So Manhattan distance is how you move from one location and reach to the other location. So this is called how you calculate Manhattan distance. So here we start from here, so distance 0, then 0 plus 1, 0 plus, 1 plus 0 plus 1, then 1 plus 1, then 1 plus 1 plus 1, and so on. It means that how many moves you are taking to reach to a certain position. But those moves should be the shortest move. Whether, if for example, this here there was no move, I mean you cannot move, but still for Manhattan you will take this shortest path. Like I given an example for the distance case. So it means that heuristic is very important. Now, search algorithm which use heuristic to guide search are called heuristic search algorithms or informed. So heuristic is one of the example of informed searches. Okay, let's not waste time and move to the first example, which is called greedy best first search. By its name, previously uniform cost search, its name was telling that we're going to deal with the cost, the true cost of the path. Okay, one last thing, that whenever you will see any diagram, if you see anything between nodes, that is path cost, G of n, and if there is anything written just right to the node, for example 10 or 12, this would be your heuristic. So this is by definition that if you see anything written by the node, you will consider that this is the distance of this specific node from the goal. Whereas the between two lines, this would be the path cost from here to here, then here to here. But how are you going to calculate path cost from here to here? Add up all together, right? So this is your cost, true cost, and then the whole would be the path cost. Now, as I explained to you that heuristic is somehow an approximate of a distance. So consider that you want to reach to the goal and you have 5 paths to go, move from one to other. And the only thing you know, if for example I consider I have 2 paths, and within 2 paths I have 8 or 9 stops. And if for example each stop is labeled with a heuristic, it means that if each stop is approximated with a distance to the goal, I can say, okay, if I say that this. So if for example this was 100, if this is 90, if this is 80, if this is 111, so it means that this 100 is distance from the goal, this 90 is distance from the goal, this 111 is distance from the goal. So it means that greedy based search says that we will move towards the node which has lower heuristic, which makes sense. It means that if we are choosing to jump towards the node which has low heuristic value, it means that we are somehow moving closer to the goal, right? Because what is heuristic? Heuristic is the distance from the certain point to the goal. So if, for example, I am at 100, which way I should follow? I should jump towards 80. This is the heuristic. Then again, at this point, I will look for all other options. So if, for example, this was at 70, so I will jump here. But I can see this is at 90. So this is how you use heuristic and you move on. So greedy based first search expand the node that is closest to the goal as determined by a heuristic function. And as I explained previously that a heuristic function is a distance, Manhattan distance. But since this heuristic function is an estimate, so your search problem would largely be dependent on the selection of your algorithm. So it is highly possible that maybe the path you are selecting is not optimal. Why? If at the moment you can see that I have just drawn the heuristics, but if for example this path, the actual cost of the path was 200. If for example for this specific path from here to here the cost was 10. So now you see, I mean, considering heuristic, yes, I am moving from here to here. But in terms of optimality, maybe this path is more costly. We will see later on example and it will be more clear. But the only thing is, I wanted to say is that the performance of your algorithm would be largely dependent on the type of heuristic function that you are going to choose. And then again, the same example that in case of a maze, a puzzle, the heuristic would be a Manhattan distance. Let's take an example. It would further clarify. So here you can see that at the moment we are using only heuristic. We are not seeing any path cost. Later on we will see that how it can affect ourselves, and then we're going to include cost as well. Okay. So you can see that we have different nodes, and here this is the same example as we done in the case of uniform cost path search. Your goal is Z and L. But normally we say that as soon as we reach the first goal, the algorithm stops. So it means that H estimated cost from state N to the closest goal. So it means that these nodes are labeled with the distance from the goal. Now there can be a question in your mind that although you can see numbers at the moment here, but how are we going to find them, right? So as I said that this can be based on certain good assumptions. For example, in the case of cities, I said take a straight line distance. So you will use some known information from the world to calculate those heuristics. So it means that these numbers doesn't come from nowhere. They come from certain good approximation. We will calculate these numbers in the next example to show you that how we're going to do that. But first, let's understand this example. So in this case, you can see that we are at this point, at the initial point, and we want to reach to the goal, and we're going to use greedy based first search. H, as we said, is distance between state and the closest goal, and all these nodes are labeled with H value. Right. Okay. Goal is to reach to Z or L, whichever comes first. So starting from the very first one. If you start from the C point, it's any point. So here you can see that the distance from the goal is 21. But this is the starting point, we cannot do anything. But if we look further, you can see that we have various options. So same as we have done in the previous cases, we can, in case of uniform cost search, we draw a frontier and we try to put everything. So here what I can do, I can put all of these in terms of heuristic. Previously we were putting them as a cost. So here for T, the heuristic is 5, for O, heuristic is 7, E is 12, B is 14, P is 15. So which node should I select at first based on our discussion? T, right? Because it has the lowest heuristic. It means that this node is closest to the goal. So what we're going to do, we're going to move towards T. But then once you expand any node, you check whether it is a goal node or not, and clearly it is not a goal node. So we're going to put it in the explore set so we don't move it back to this node. Now from this T point, what are the options? The options are B, O, E, P. I will not write it again, but clearly we can see that who is the winner here? O, right? Because O is 7, E is 12. So it means that we're going to move towards O and again check whether it is optimal, whether it is goal node or not, and clearly this is not. So from O, what are the other options? The other options are, this is already explored. I should have marked it with some blue or some other color, but sorry for this. So this means that this is already explored. Now the other options are B, I, N, E, P, right? So based on heuristic, who is the winner? I is the winner, right? It means that we can move towards I. And then finally, again, if we look for the other options, so we have all these options. We can have N, E, P, B. So it means that we cannot go to this, we cannot go to this. It means that clearly we will go to 0. So it means that here goal is found. But, so this is how we move based on certain heuristics. But we'll see in a while that this can be, we'll see in a while that this can be a problem. But before that, let's do another example. This is a very good example. So, imagine that you have a puzzle. This is the initial state, and you want to reach to a goal state. So you know the initial and the goal state. So we want to see how our algorithm works, because in the previous case, we were given the information about the nodes with h value. Here we're going to calculate the h value. And as I said that in case of puzzles, the only option is to move from here to here, or this is the only option. So how, basically here I'm explaining it, but this algorithm will be given to any coding or any AI agent, and it will be trained on the same logic, and then it will do all the iterations and give you the answer. So if I look at the initial state, what are the possible next states? So the possible next states is either I move 2 here, this can be a possible state, right? Either I can move 7 here, this can be a possible state, or either I can move 8 here, this can be a possible state. This is, okay. So if I look further at them, so from here I can see that either 2 can move here, one side, 3 can move here, can be another move, 5 can move here, another move, 6 can move another. So I get, so from this point, you can see that we have 4 possibilities. Similarly, if I come here, 6 can go here or 7 can go here. These are the only possibilities, right? If you want to expand further. And same goes here, either 5 can come here or 8 can come here. Okay. So it's mean that here we have 4 possibilities, 2 possibilities, 2 possibilities. But at the moment we don't know which direction to move. So we're going to use a criteria which is called Manhattan. Manhattan priority function, or simply Manhattan function. In order to do the calculations for Manhattan function, what we're going to do, so we have several options. So we have 1, 2, 3, 4, 5, 6, 7, and 8. These are the numbers that I have in the puzzle, right? So now how are we going to calculate the Manhattan function? We're going to take the first, we're going to see the moves. So how are we going to start? We're going to start with each number for each possibility. So this is possibility number 1. So what we're going to do, we're going to compare this with the goal node. And we will see for each number that how many moves I can do to get the number at the same location as of the goal. So if I look at 1, you can see that 1 is the same location as in the goal. So it means that for 1, I need 0 moves. Similarly, if I look at 2, so 2 is at this location. So I can go from 1, 2 or 1, 2. Both are the same distance. So it means that for 2, I need 2 moves. How many moves I need for 3? How many moves I need for 3?
3.
Yes, because 1, 2, 3 or 1, 2, 3. Then how many for 4?
1.
1 move. Because we simply need to move from here to here. For 5?
1.
1 move, good. How many for 6?
2.
For 6 we need 2. Here and here. And for 7,
2.
again 2. How much for 8?
3.
Yeah, for 8 it's 3. Right. So how are we going to calculate the Manhattan distance? Simply add all of them. No, we're not going to do it now. Okay, so it means that for any state, MA, this is 14. It means that for this, Manhattan is 14. Now we're going to try for the second state. So how many moves for 1? 0. How many for 2? 1. For 3?
3.
1, 2, 3. For 4?
1.
5.
1.
Okay. 6.
2.
7.
3.
3. And 8. 3. So again for this state it would be 14. Which means that for this is 14 as well. going to see for state number 3. How many moves? Calculate Manhattan for state 3 yourself.
Okay.
Calculate Manhattan for yourself for state 3. It's just that how many moves you need for each number to reach to the goal, and just add all of them.
Is it 14?
Sorry?
Is it 14?
No.
Oh.
12, right? Yes. Anyone else? How much is the M for third case?
12.
Oh.
12, right?
What's the
So
number?
for case number 3, this is 12.
Oh.
Okay? Right?
Yeah, yes, I just saw that 1 doesn't need to move. I don't know why I wrote 1. No movement.
Right. So it means that based on this, I don't want to explore these states, rather I can choose this state. And now when I come to this state, again I will be having 2 more states, and I will do the same Manhattan, and this is how we're going to reach towards the goal. This is how actually this algorithm works. Okay, so here is the same favorite example we doing in every search algorithm. So again, we have to reach from point A to point B. We already done this with other search algorithms. For example, for depth first search, we move from here, went to depth, another depth, and we move towards point B. So in this case, we're going to use a Manhattan function. So before that, let's see what is a Manhattan function. We already know, but let's see again. So let's say you are at a certain point C or a certain point D. So how are you going to calculate a Manhattan? Because what we say, whatever nodes or whatever possible options we have, we calculate Manhattan at every option, right? So for example, in the previous case, we calculated Manhattan at each node, at each state. If you go back to the previous state, you see that every node was labeled with a Manhattan. So here, what are your nodes? This is 1 move, 2 moves. So at every move, you have to calculate the Manhattan for this problem. So Manhattan, as I said, is the shortest distance to the goal, whether some moves are possible or not, right? So here you can see that what could be the Manhattan? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It means that if I am here and if I want to reach here, I need to move 15 moves. So it means that Manhattan, or I can label this node as 15. Similarly, if I'm at A and I want to go to point B, I can calculate the Manhattan distance for this problem. So if we somehow calculate the Manhattan distance, like I said, if you remember this point C, so we calculated it as 15. If I select this point, so 1, 2, 3, 4, 5, and 6. So 6 move was to reach the final point. So it means that this is how we calculate the Manhattan function. At each point, we're going to calculate the shortest distance. So if, for example, I'm here, I can take this point and I can reach to the, this could be my shortest distance. Now, we will move from one node or one position to the other position based on Manhattan. So here, I don't have any other options. I have to move to 19. Then, until 15, I don't have any option, right? But after 15, I do have options. So which way I should choose here? Which point I should jump to?
14.
To 14 or 15? Which one for us?
14?
Yes, 14, because we want to choose a value of low heuristic, right?
Yeah.
Whichever is low. That means that we move towards 14, but at the same time, like I said, when I'm going to move to 14, I will also look on other nodes, whichever nodes are possible. So 8, 14, 16 was also possible, 13 was also possible, but 13 was low heuristic. When I move to 13, again 16 and 12. When I move to 12, again, and I reach to point A. If I keep on moving, because even if I'm here at 8 point, I have the option, I can go here as well, I can go here as well. The first thing is that we can choose any direction. Normally, I mean, even in such cases, we take a rule that we first go to the left and then go to the right. But we can choose any rule if we have any problems at certain point. So when I reach to point 8, you can see that 9 is higher value of heuristic, where 7 is low. So I move towards this one. Next is when I move to this point, you can see that clearly 5, 4, 3, 2 was the lower value. I moved up, but then I came to know, and then finally I saw that this was the final solution. But clearly you can see that in this case this was the redundant path. But if you compare it with the breadth first and depth first search algorithm, there were many redundant paths. If you remember, we moved toward this, we moved toward this. So it means that here we are just exploring more or less in the right direction. Here we have another example which will show us that we are slightly, we only using heuristic, we are taking more moves. So in this case, you can see clearly that we are somehow taking reasonable moves to this was the only possible shortest path to the goal in this case, right? But if I come here, looking at this with eyes, I can see that this can be the shortest path, right? Because this clearly takes less number of moves. At the moment, we are not considering path, right? We are only considering heuristic value, distance of a certain node from the final goal. So let's calculate the Manhattan. So if I calculate the Manhattan, clearly you can see that this node takes one value and reach to the goal, this needs 2, and so on. Similarly, this node takes 17 values to reach to the goal, whichever path is the shortest to reach to the goal. So based on the heuristic value, I can move clearly to 13. After 13, I will see 12, 14, clearly 12, clearly 11, 10, 9, keep on moving, and you will see that at all locations, if you keep on comparing, you will never go to 14, right? Because at each location, you can clearly see that your numbers are less than 14. So it means that you're going to choose this path, which somehow looks that, although we use, because as I said that, the accuracy of your algorithm is strictly dependent on the heuristic you're going to choose. So in this case, you can see that you are choosing a long path based on heuristic. So that's why we say that only Manhattan function is not leading us with the best possible path as it is leading a long path. So it means that only heuristic is not a very reasonable option to move forward. But if, for example, you have a greedy algorithm, if you are being asked to find certain paths with greedy algorithm, you only need to consider heuristic. You don't need to work out in your head about the path, because when you will get a certain question in exam, that question will be enriched for all the options. It will have path cost, it will have heuristic, but if, for example, someone asks you to find best first search, you don't need heuristic, you don't need path cost, right? But for greedy algorithm, you will need heuristic. So choose whatever you need and then find the path. So if it was greedy best first search, so this was the only path that I was supposed to choose. So it means that in addition to heuristic, clearly we can see that we need something else. And at the moment, it comes to my mind that can be path cost. In case of this puzzle, what is path cost? The number of moves you take to reach to the point. In case of a city, it is the actual distance between the cities, right? But in case of puzzle. It is the number of moves that I am taking to reach the goal is actually the cost for my problem, right? So it means that if I somehow use heuristic as well as the cost, this can improve my algorithm. So here comes A star algorithm. So A star algorithm is just an extension of greedy best algorithm. And in this case, we are not only using h of n, which is heuristic, but we are also using the path cost, which is g of n, as we defined previously. So if I say overall, what is my evaluation function? What should I look at to decide? I should look at the sum of h of n and g of n. And whoever comes low, we will move to their side. So here, what is queuing function? Queuing function is queuing function sort by a function. So it means that previously it was FIFO or last in first out, then we moved toward cost so far. Then in the previous case it was based on heuristic, and now the queuing function is based on certain function which is combination of heuristic and path cost. So in this case, as I said that at each point the algorithm will consider two things: cost of the path to that node and heuristic value at that node. And then we will see whether we should keep on moving in this direction, because if I consider this example, we will do it in a while, that if I reach a certain location, I will see that the number of moves plus the heuristic would be greater than the number of moves here plus heuristic, right? So here you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 plus 6, and here 14 plus something. Or if you go further, we'll lose the optimality. Right, so doing the same example. Again, heuristic is Manhattan distance, write down all distance to go from any current state as we studied previously. And now, while moving from one node to another node, we will find evaluation function. What is the evaluation function? Evaluation function is h of n plus g of n. G of n would be, if for example I am here, it would be 1, 1, 1. So 1 plus 1 plus 1 would be the cost, because g of n is cost from initial state to the current node, whereas heuristic would be the value at that instant, whatever is the heuristic value. Okay, so the very first option was to move to this point. There was no other option, so it means that here I have 17 plus 1. The heuristic was 17, and now plus 1 is 1 move. Then 16, when I move to 16, it would be 2 moves. 15 plus 3, 14 plus 4, 13 plus 5. So now here is the deciding point, right? So it means that here I have two options. 13 plus 6, sorry, 12 plus 6 is this option, and there is another option which is going this side, which is 14 plus 6. It means that here I have 20 and here I have 18, right? This is our evaluation function. So it means that I should go to 14, right? No, I should go to 12, because the evaluation function has low value. So 12 plus 6, 18. Then 11 plus 7. 11 plus 7 again 18. Then 10 plus 8, 18. 9 plus 9, 8 plus 10. 15 plus 5 is 20. Okay. So when we reach to this point, now I have options further. So as I said that we can decide something. So when I reach this point, it was 15 plus 5. I keep on digging in the same direction, or I can move to the left, which is 14 plus 6, 20, both of 20. So I move to this point, but the next one should be this one, right? Why? Because if I am moving further, 16 plus 6 is 22, whereas 16 plus 14 plus 6 is 20, so it's low. Again, at this point I will look here and here. This is 22, and this is 22. So I can keep on moving in the same direction, or whatever you decide. Like in the previous case, we decide that we will we will select moving towards right. So that's why I selected right. But it could be that you say, okay, first if there is a balance or if there is a draw, then which direction you should move. So here we saw that there was a draw. At this point there was a draw here, and here we said no, keep moving on in the same right direction. Okay. Now it means that we will go to that direction, but next is 17 plus 7, which is 22. 17 plus 7 is not 22, 23, and 15 plus 7 is 22. So it will move in this direction, and then except that here you will see that all the heuristics are low. So it means that it stopped moving in that direction, and it has decided that see, this is the shortest path to the goal. So it means that, and it was clearly mean, even if we forget about the calculations at the moment, it makes sense in our mind that if we choose heuristic, which is lowest distance to the goal, plus the path cost, the number of moves, it will give us a complete function which will always reach to the optimal point, mean the optimal solution, the goal which takes least time to reach to the least function value to reach to the goal. Okay, so if for example you have this example, you want to move from point S to G, can you please find the path that an A star search algorithm will find?
In which way? Holistic way?
A star.
A star.
Yeah. A star is, you know what it is. Heuristic plus the path cost.
So the A star would be the
S is the starting point.
H plus G, right?
S is the starting point. Yeah, so from here you can see you have two options. So each option you will calculate S plus G. So calculate and tell me what is the path.
you have to have each node in each.
So whichever node you are, you have to move to the next node, right?
And then add all together.
So what you're going to do, you're going to check for A and you're going to check for D, because these are two possibilities. At A, you're going to calculate the function, which is 9 plus 3. Similarly, at D, you're going to calculate function, which is 5 plus 2.
And this starting 7 we don't
Starting now, the starting we don't need, because at starting you have 7 plus 0. Starting is mean you have no choice to start. So which is the first node I will going to jump?
D?
It's going to be from S to D.
D. Why?
Because it's a solution.
5 plus 2, right?
Yeah, 5 plus 2, 7, right? Yes. And now from D you have again two options. You have three options basically. This, and this, right?
Yeah, but I will choose.
D?
It's a D to P.
Well, D to B or D to E. So,
D to E.
D to E.
No, no.
D to B.
Yeah.
D to B to
Yeah.
E, then E to E.
D to B.
So S, D, B, and then.
Cheat, yeah. Cheat. Because we.
Oh, okay.
Our endpoint
Oh,
should be cheat, right?
Sorry?
Cheat. That's our endpoint.
You're asking me what the goal is G, right?
The goal is cheat.
Yes, you see from S to G.
Yeah.
Okay.
So G is your goal.
So S to E, D
Okay,
to B,
question.
D to E,
What if it's the same
D
value?
to cheat.
Hmm?
What if it's like the paths are the same?
The issues whatever.
Ah.
If the moves are mean,
Shortest always look better.
yeah, if you're saying each path has cost 1,
Mm.
then mean they are equally spaced. So then clearly you will also look at Manhattan, but this the x distance,
Yeah.
but then the less number of connections will lead to the road. So what is path here?
DBCG.
Why do you go for C? Why?
Wait, what?
No.
Why not D, B, E, G?
Okay.
Is
So D, B, E, G.
that's what I was thinking too.
That's the shortest way to reach the goal.
No, you don't need to look at the shortest goal by your eyes. You need to consider h plus g to reach the goal, right?
Okay.
So I'm not sure which is, so here I can see it's 7 and
No.
here it's,
Yeah, but even if
12.
the physical trait of H plus G,
so I will move to 7, right?
Yeah.
Then I can see here is 7 and here is 5. So I will move to this point.
which
Okay.
is 5.
Yes. Now from this point to the next point is 4
Yep.
And
and from here to here
It's also 4.
Is for
4, yeah. So we can move in any direction for the moment. So if for example I come here, I can select 3 plus 0 and here it's 4 plus 0. So which way I should follow?
3 plus 0.
Yes. So it means that S, D, B, E, G,
G.
right? So you can see now that when there is equality, it doesn't matter which way you should go. It will ultimately bring you to the one which satisfies the condition. So choose any one and then you can move.
You know, this kind of algorithm they use in networking. You know, when they focus not to know.
Yes, to find nodes actually, yeah.
But one question: if you already reached the goal, it's more expensive to go back and then rearrange it.
Yeah, good question, by the way, so that I can clarify your, although I explained this in previously, but this is a very good question. See, when we are here or here, we are just checking to see how much would be the function, but what we are not expanding it. It means that here I check that going to here would cost me 4, here going to here would cost me 4. But it will cost me only when I go to that goal via that path. At the moment I am just checking. Here you can see that I checked here and then I chose this one. So again here I am just checking which one is good. But it will cost me only when I will expand it. Right? So it means that when I came here, I never moved here. Why? Because the distance was not allowing me to do that. But here it allowed me, then I jumped here. Right? So it means that here we are not jumping. So you will not be charged as if you reach the goal, then the problem is finished. You cannot come back. So it means that you are not choosing this direction. You are only checking this. It means that you are only putting this information in the frontier. It means that you are putting information that G can be 3 and G can be 4. So you will choose G3 and not 4. So it means that you are just selecting it and not expanding it. And you will be charged only when you will expand it. Okay? You can see that this is how, if you get something in the exam and looking at the marks, or if there is an instruction that show work or something, then you can show your work in this way. This can be one way, or even if you show, okay, you can write 5 plus 7, no, there's something to show that how you reach to the final goal and not just that you reached it. That would be safe. Because sometimes you can reach to the goal just by
By inspection.
Visualizing. Yeah.
or by visualizing the surrounding people who are sitting next to each other, right? Yeah. Okay. So here comes very important property for A star algorithm. which explains about when this algorithm would be optimal. As I said that in greedy based search, we said that the performance of your algorithm depends on heuristic. If your heuristic is good or a very accurate estimate, then it will perform better. But if heuristic is not, then it will. So you can see that heuristic jumps into A star as well. So it means that again, A star performance is also dependent on the heuristic. So it means that we need to find a way, we need to see a way to tell whether a solution is optimal or not. And it will strictly depend on the, we'll see in few examples that it will strictly depend on the value of the heuristic. If for example, I'm saying that I'm going from here to King Cross and I estimate distance as 10 kilometers, for example, and whereas the actual was 5 kilometers. So it means that the estimate I took is not an accurate estimate. So it means that my problem can go some other direction. So it means that heuristic is very important to consider. So we say that an A star search is optimal. It will be optimal if it satisfies two conditions. One is called admissibility, and the second one is called consistent. Admissibility, as I just stated with an example, that how close is your heuristic to the true cost of the path. So if, for example, like I said, in previous example, when we moving from Cebu or whatever to Bucharest, I don't know why you're from Romania, right?
Yeah.
I don't know why they chosen this Romania. In every example, there are
I think it's the
Romania.
textbook.
Yes. Okay. Right. So it means that if, for example, I estimated here it's 100. What does it mean? It means that the shortest path I'm considering from S to the goal is 100, right? Whereas if, for example, I use the true path, the actual distance, if, for example, I'm just taking example 10, 10, 20. So it means the actual cost is 40. It means that my heuristic was overestimating the cost. It was way beyond. So it means that if your heuristic is overestimating the cost, it means that if the cost estimated by heuristic is greater than the true cost of the path, it means that your algorithm would not be optimal. It will not choose the optimal path because your estimation is not correct. So it means that we will say that h of n is admissible when it underestimate or estimate true cost equal to true cost. So it means that we will say that if the h of n is less than or equal to, then we can say that okay, it is admissible. So that's why we say that never overestimate the true cost to reach the goal, or must underestimate or be equal to the true cost. So this is the condition for admissibility. Overestimate is not a problem. Still you can go towards optimality, but if underestimate is not a problem, but overestimate is a problem. Now the second thing is consistent. So it means that admissibility was related to heuristic directly. Whether this chosen heuristic is admissible or not, allowed or not. The consistency is basically dependent on heuristic plus cost, both. So if, for example, n is your state this, and n prime is any successor state, any next state. So consistent means that as you moving forward, for example, you are at certain point, if you are taking heuristic at the next point and you are adding cost to it, it should be greater than the previous heuristic. So which means that the estimated path cost to the goal of a new node in addition to cost of transition to it from the previous node is greater or equal to the estimated path cost of the goal of the previous node. So this condition should satisfy for consistency, that your algorithm is consistent. Mean at each point, your cost is adding up. So if it is consistently moving forward, so it means that at each point your sum would be higher. Why? At each point you are taking certain moves. So if it is not consistent, so it means that it can bounce back and it can be less than the previous one, which is not a consistent thing, which is not following a pattern for moving to the next point. Let's take an example. So you have seen that here the condition for consistency and admissible. Admissible, we will see now it is straight away. But in this case, you can choose two ways. Either you can say h of n minus h of n prime less than equal to c, or we can say that the difference of the current state minus the next state is less than the cost. I mean, this is more clear to visualize, or if you want to use this way, it's still fine. So if you get it in the exam, you can use either way. You can use this equation, or you can use simply that. If you're using this equation, it's better to visualize. But here in this example, I've just used the same way, which is the original condition. Okay. So you can get something similar in the exam. The very first thing can be provide condition for admissible and consistent heuristic. And you all know that. You can clearly say that a heuristic is admissible when it never overestimates the cost. Or you can say another definition, it should underestimate the cost. So this is clear. And a consistent heuristic is if your n is the current node and n is the next node, then we say that the path cost from this node to the next node plus the heuristic should be greater than the heuristic of the previous node. So this is the condition for admissibility and consistency. So let's start. You have two heuristics given here. We have heuristic h1. It means that here it should be 5, 3, 6, 6 here, 2, 3, and so on. Similarly, there is a second heuristic. So, admissibility we're going to check by looking the true cost. The true cost means the cost that an algorithm going to find. Okay, so if I look at the true cost, so you can see that this is at state S. If I write this one, this is 5, 3, 6, 2, this is 3, and this is your goal. This is your goal state, right? So it means that this heuristic is telling me that the estimate of distance, shortest distance from initial point to the goal is 5, right? Shortest distance. Let's see the shortest distance. So the shortest distance that I can see is 1, 2, 3.
What? Isn't it just 1 and 2?
Okay, so you can see that S to A to C, and C to G. So you can see that 1 plus 1 plus 2 is 4. So it means that if we looked at the shortest distance, so clearly we can see that the shortest distance is 4. Whereas our heuristic is telling us that the shortest distance is 5. So it means that this heuristic is clearly not admissible, right? So this is the way how you're going to check admissibility. And the same way you're going to answer that, you can write H1 overestimate the cost. You can use different wording, doesn't matter. S to G, A is 5 when it is 4, so it is inadmissible, clearly. Then the second thing is let's check the admissibility for H2 as well. And then we will see, we'll move to the consistent. So this part, and now we are going to see the admissibility. So is H2 admissible or not? So you can check heuristic value from any node, but if any node is not satisfying the shortest distance condition, then the whole heuristic would be inadmissible. Okay? Yeah. So you can see that H2 is this one. So in case of H2, your S is 4. In the case of H2, your S is 4. I will not mean the other things I can write, I will just remove them for a while. So again, you can see that the shortest distance is 1, 1 and 4. So it means that heuristic 2 is not overestimating it. So it means that I can clearly say that H2 does not overestimate the cost and is admissible. So this is how we check the admissibility. But you can check admissibility at each node. For example, you can see that if I check at A, it's 1 and 2, 3. So you can see that, which one is this? And D. So from D to G, you can see that it's saying 3. So what is heuristic value? So it's 3 from, okay. Okay, so see at A it's saying that 1 plus 1 and 2, 3. So you can see the heuristic value is 2. But we said that even if it underestimates, still it is admissible. So you can see that here it was supposed to be 3, but it is underestimating, so still the heuristic is admissible. So you can check at each point. So if I do for this thing, so at S, the true distance is 4. Here, so at point A, the true distance is 3. At point B, the shortest distance is 3 and 3, 6. At point C, the shortest distance is 2. At point D, the shortest distance is 3. So you can see that it is equal to 4, less than 3, equal to 6, less than 2, equal to 3. So it means that overall the whole heuristic is admissible. But if at any point this condition is broken, the whole heuristic would be inadmissible. Okay? Right. So it means that H1 is inadmissible, whereas H2 is admissible. The next thing is to see whether it is consistent or not. How are we going to check the consistency at each? For example, if I want to check it, if it is consistent at A or not, so what I am going to do, so it means that H at S should be less than equal to H at A plus cost of S to A. This is how we find the consistency, that heuristic of the initial state, then heuristic of the next state, plus the path cost between the two states. Okay, this should be the right hand side should be greater than that. So in this case, you can see that the starting heuristic is 5. If I check H1, so this is 5, and the heuristic for the next state, which is A, is 3, and the path cost is 1. Is it a true condition? No, right? 5 is not less than equal to 3. That means that it is not satisfying the consistent condition. So it means that overall, if we use this heuristic, we can still use it, but it will not give us an optimal solution. Okay. So it means that this is not consistent. Then if we move towards H2, okay, for H2, the H of S is 4, less than equal to for next state is 2, and path cost is 1. Again, you can see that the condition is not true. 4 is less than 3, no, this is not true. So it means that H2 is also not consistent, but H2 is admissible. So if you get something similar in the exam, you have to use the same way to answer your question, which is quite easy, I guess. It is not difficult. You just need to remember the admissibility condition, which is very clear. So if after you find the admissibility and everything, and then you are asked what path the search problem would result using the admissible heuristics. So it means that now it is being asked to you that between H1 and H2, take the admissible heuristic and find the path, whichever path you will find. So what path it will follow if I'm going to take admissible heuristic? Which one was admissible? Which heuristic was admissible? Number 2, right? So H2 does not admissible. So it's saying that out of H1, because again, for finding a path for A star algorithm, we need to have a heuristic. Here you have 2 heuristics, but in the question, once you have found all the things, the next question was to find the path. So how are you going to find the path? You simply need to put the heuristic values for H2. So 4, 2, 6, 1, 3, and 0. So now we're going to use the same method. So I will move to A. Right. So here you can see that I need to calculate evaluation function. Evaluation function at A would be 1 path cost plus 2, 3. Similarly, if I want to take this path, which is the evaluation function at G, it would be 12 plus 0, right? These are the 2 paths I can follow, right? This one and this one. Here the heuristic value is 0 because it is goal, but the path cost is 12. So you can see that here the heuristic value is 2 and path cost is 1. So definitely I will look for path A. So I will move to path A. Now the next thing is from path A, I can go to either B or C. Again, I will look for heuristic. So 1 plus 1, 2, 3 plus 6. So definitely I will follow this path, and ultimately you will see that will follow SACG, which is the short path. Take a 5-minute break and then we will start another.
I haven't used to take breaks.
Yeah, that's true. Man, I'm struggling
My keys just broke, like I need the keys. I only have the phone. It's very light.
feels like it. Feels like it doesn't have it.
Yeah, it's light. It was like long time. Like never used like this without the case. It feels heavy with the case. Even yours, like it's light. But with the case, it looks better. It looks protected. This one looks
Now I feel it.
For the basis, yeah. Without 50, like, yeah, what you want.
Let me ask a question. I think you.
What you get?
How you talking
What's
about?
asking you?
43.
What did you
I
get?
was asking something like.
100?
Yeah. No, max.
50, 50.
50.
That's good. What about you, vegan?
45.
Okay.
Wait, really? I thought you like slept.
Yeah,
At
did
library.
she give you a grade in the post?
But library, that's what I studied. She got 45.
Yeah, it worked. It worked.
You're gonna have a meeting?
He said that he went to the completely wrong side.
How does that?
Because
It's so cold.
You cold?
I'm not cold. I'm just kind of.
Maybe because you're having some
Yeah, actually.
or drink like a drink.
Yeah. Also, it's like.
And he says he's gonna
Kinda
give you
dark.
yeah, he's gonna tell me tomorrow.
I mean, isn't that fun? Like seeing others drinking.
He doesn't reply.
Mm.
They both don't
Oh, you
reply.
in the same group?
And then they ask me why you don't
I'm
come.
ready for this.
You don't reply.
You know
What
what?
should I say?
My dad used to tell me
Mm.
when he was in Afghanistan
Mm.
with the soldiers in the field.
Mm.
He used to like drink or eat like outside of the Afghan soldiers too because of this reason. Yeah, because they were standing in the sun. The desert was kind of hot. Like imagine drinking in the front of the sun. And they said like, don't do that.
My brain's not.
I mean, here is fine because it's not
Oh, yeah.
hot. Yeah, it's not. But imagine in the desert, like you
know,
feel thirsty to drink.
Or just imagine in the Arctic where the sun doesn't set. There is no sunset. It is in the day permanently.
One brute force attack.
Well, yeah.
Go brute force.
Okay, no problem.
Right limits.
I'm
Do you the right limit?
at 1 p.m.
How did you do it?
One person can create it.
Next week, even if it's Thursday, right? So what I can do is,
And how did you do it?
And it's a price for
I'll give you the
this.
date.
No,
Use
Friday,
the
job
box,
is like
use the box.
27,
No, but how did you
That
do
will be
it?
someone by
I'll be back in just a phone.
But how did you scan?
It's kind of focus. I'll use it tool.
And how will you close them?
Doesn't matter.
This is tool that you can use focus, you can use JWT, you can use nuclear, you can use. There's a lot of tools. You can go if you go on GitHub, there's a lot of tools. You can do some domain finder. Some domain finder.
And did you start to
Yeah,
build
okay.
You know the.
No, actually, it's just so fun. I've done some of
The
it.
last
week.
Python one, isn't it?
What did you say to you?
Also
You
for
completely wrong.
Oh, yeah.
No, they said you just focused on content.
Have you started?
That was the same.
I started that this week.
And they said,
Yeah,
well,
it's
we
not
need
too
it.
bad.
Please,
It's a
you
long
go in
it's
your own
just
way.
like-
Yeah,
You need
it's
to dance
dances.
it.
You copy and paste.
It's kinda like-
You know, last few weeks, last few weeks, I was focused on how to find it.
Like, by the way.
How to
And you
how to
have to download so
how
many
to
stuff.
find.
Virtual box and you have to do all these configurations.
You know when you do the system
You
design,
have to do
It's not really easy. You know when you do the system design, so something you have to understand all the technology. You have to understand all the doctor.
So you said
My
my
bad is
bad.
just
Yes.
start.
So literally in
Mango,
establishes, you go to
MongoDB. You have to understand all the thing. You know,
Our project is like
It's a lot.
the the cybersecurity is very important.
No,
You have to understand also networking, you have to understand all the ports. How to do
But
it.
then we have to find something.
You have to understand JavaScript, HTML.
Wait. Okay. So, bro, I suggest you just get everything down the way. Yeah, bro. Get your long start the way now.
I'm not listening, I'm not listening to anymore.
Yeah.
Let's do the
What
business.
was the other module? The one after this next
Yes,
You have to do
you don't have to
cybersecurity.
waste a lot of time on it, you know what I mean? But if I entered something new, you're gonna have to.
Cybersecurity,
That's fine.
Yeah, let's revise. Let's do the revision together.
Bro, like,
No,
do all the part of it.
What are you gonna do? What are you gonna
Is
do?
that right this morning?
Well, it takes long.
I'm-
But if you just,
21st.
if you dedicate like a good couple of days, you get it done. Because that's what I'm still getting it done now, bro. I looked at it, the like time score,
you
everything.
get-
I
you
wouldn't
get
have
the
time later
photo.
on to do it.
Where's it going?
We have the IO to get sample as well.
Black.
That's
I didn't do it, I had to do the project yesterday.
It's
How
gonna
many
be
exams?
around
Like
How
for
many
2 days I also
Only 2 exams on April. Another exams in
Say I
May.
did the project.
Plus,
Let's start with this next search method.
Some of the coding.
How many was it? Should it be?
sit
Does
down.
anyone know, wait, does anyone know how many was the project should be?
You
So
going-
the final, you know, how many?
No,
5,000?
Huh?
That's not bad.
No, what, for the final report?
I'll put
I was like 10,000.
10,000.
So I'm gonna start
You know it's next month.
Yeah.
I saw my calendar, I
Next
saw.
month, I have
Next month and I barely started this.
Okay, guys, take your seats.
2 weeks, nice.
Now we're going to move towards another search method, which is, you can see I said multi-agent. In the previous case, you can see that you start with one point and just move towards goal. So you are only one who is playing or finding something. But now we're going to move towards one of the search methods, which is called adversarial search, and it is multi-agent. And from its name, you can somehow guess that it will work always to oppose the opponent, to oppose the other player. So it means that you have 2 agents playing with each other, and what you want, if one is winning, the other one will lose. So the TikTok, the famous game example, so you can see that in this case, one will be trying to win, but at the same time, if he's winning, he will try to, he is making the other one lose, and same goes for others. So it means that in this case, it could be one player gains strength, the other player will lose it, and vice versa. But the sum of 2 strengths is always 0. Makes sense that if one is pushing in one direction, the other one in opposite direction, so the sum of the strength will be 0. So that's why these are also referred, specifically this TikTok game, the 2-player game, this is also called zero-sum games. So how this is done? If, for example, we start from a certain location, how we execute, how to choose the next move, and what to do. So for this case, we use this minimax algorithm. Minimax algorithm is if, for example, one player is max and the other player is min. That means that max player will take all those moves which will maximize its strength, whereas the min will take all those moves which will minimize the other strength. In other words, it is maximizing its own strength. So if we take as a layman example, so if one is making a move to reach to the goal, the other will stop it. If, for example, you can see if in TikTok game, if someone has 2 circles here, so if it's your move, you're going to block it by putting a cross here. So this is how we say in the one agent is max agent, the other agent is min agent. So here max, since it is a big cross game, so max is the cross agent, the cross player, and 0 is the min is the circle player. Okay. Now to understand this problem again, as you all know that whenever we're going to define any problem in AI or search algorithm, we define it by certain things. For example, initial state, environment, and so on. So in this case, we have initial state. What is initial state? We all know that it would be an empty box. It would be something like this. This would be initial state. Then it can be player 1 move or player 2 move, depending on any logic. For example, in the first move, I can be the first one. In the next round, the other player would be the first one. So this players of S is a function which will tell whose turn is this. So at any state, this player would tell whether it's player number X or player number circle, max or min. What is action? Action is, if for example, I am putting a cross here, so now there are many actions that a circle can do. It can put here, 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 here. So these are all possible actions that a circle can take, but how it's going to take, that is another story. We'll do that in a while. But these are the actions. Then what is results? So if, for example, this is one action, so I will be, if for example I want to take this action, so I will take this action and this would be my final tick cross game looks like. Then terminal. How we define a terminal is multi-agent, so any state after which we can say game is over. If for example, where the circle is winning or cross is winning, game is over. If for example, our terminal is something else or reaching a certain location, or if for example, in a cricket match or football match, your terminal is that if the goals are reached in a certain number of time, if not, it means that one team will win and the other team will lose. So terminal would be the condition which would decide whether the game is ended or not. And then comes the utility. Utility will tell based on the terminal state. If for example, for one football team it was 3 and for other it was 2, then the utility will analyze, it will see, okay, utility of the game is, of course, the 3-1 would be winner. So then the utility function will give you the output. For example, for the case of tick cross game, the utility will see that whether cross moved, if cross has moved, it will assign a certain number. If circle has moved, it assigns a certain number. If there is a draw, it will assign 0. We'll see it in a while. So the initial state will look like this, as we all know. Then if you move further, so considering any state, it can be any state. So this player function, what it will do, it will take any state and will decide whose turn is it. If for example, this was given to the player, to the game deciding player, it will answer that the next turn is for the circle, right? Considering the state. But so it can be that considering, for example, you can see that here it was a cross, so it said that the next move is for the circle. Then as I said, what are the actions? So if you have this condition, the possible state space for the actions is you can put a circle here or you can put a circle here. But then these are the possible actions. And what you have to do? I don't know where the result slide went, but anyway. So if I write result, so what would be result? Result would be this state, comma, whatever action it is. So if I'm saying I'm going to take this action, so how it will look like? This result function will look like 0, x, 0, 0, comma. What is the action? The action is that put circle here. So it will result, the final state will look like this one. So it means that taking the action, applying it on a state would give you a new state, which would be this one. This would be your result. Then again, as I said, terminal state. What can be a terminal state? Terminal state can be a winning state or a draw. So a winning state will be attributed as true and draw state would be attributed as false. So, or in other words, if we are at this point, so we cannot draw any conclusion from here, right? Because still there are moves pending. So it will say no, the game is not ended. It means that there is no terminal at the moment. So it will keep on playing. And if it is true, it means that we have reached a certain location. And then finally, utility function. So utility function is when you have a terminal state. So you can see that here you can see you have a winning position. So it means that you have a terminal state, you provide it to utility, and utility assigned it one value, one mean max has 1. And if you have utility assigning -1, so it means that min has 1. Why? Because it tried to minimize the outcome. So indirectly it is maximizing itself. So if we say. And if for example the move was in such a way that you have two possible winning states, for example, you can see that this can be or this can be, still your value would be 1 because it is still a 1 case. But if you are not reaching a terminal state, you will always get a false condition, except that it is a winning state. So your terminal state would always be decided based on certain things. But if, for example, I reached a state which was not terminal, if for example there was a state where it was a cross, here it was a circle, here it was a circle, like this one. So you can see that no one is winning. Again, this is a terminal state, but the function will desert the value as 0, that this is no win, this is not. So this is how we define a tick-tock problem, or so it means that if I summarize all the things that I've just said, so we start from for a puzzle, we start from an initial state. The next state is, so at this point it says that max x, it means that x will do the turn. So that's why x can do turn on all these locations. So these are the possible. At this point, min has the turn. So min has all the possibilities, and keep on, and it will move on until it will reach the terminal condition. But how these states, how these conditions will be decided, this will be based on some algorithm, and we will see that will be based on minimum and maximum algorithm. So let's say that we started from a certain location, from this point. So you can see that clearly we have 1, 2, 3, 4. So mean the next turn is for player 0, player circle. So now we will see that what are different positions for the circle. So circle can go here and circle can go here. But if circle goes here, in the next move, cross can win, right? So it means that if circle goes here, the max value would be 1 in the next state. So that's why we say that this is just analyzing the state. We are not moving to any state. So it means that if circle goes here, max value would be 1. But what is the function of minimum? Minimum is always trying to minimize the max value. It means that what does minimizing in this case mean? Means bringing it to 0, right? Because there are only two states. So it means that if it has chosen this value, it will minimize the max value, right? Because it can, at this stage, I can see that in the next turn, max cannot gain any value. So it means that max will gain 0. So it means there is no benefit for the max. So it means that looking at this, I can say that I can move in this direction. However, if, for example, the min has chosen the wrong move, and if min has put it here, so it means that here it has maximized the opportunity for cross player to win, the max player to win, and clearly you can see that in the next move it will win. So it means that this is not the possibility for player circle for the movement. It means that this is the only possibility, and you can see that when it has placed circle here. So in the next move, you can see that the overall game was draw, and the value of the when you given this to the terminal function, it said yes, true, because it is a terminal state. And when this terminal state was given to utility decided whether it was win for max, win for min, or a draw. And utility function given a value as 0, which means that it is a draw case. Similarly, in this example. Sorry?
This is like a neural network.
Yeah. So in this example, you can see that you have from this, the next move you can take is for the cross. So we can define who is the next move. So at the moment it is a move for the cross. So you can see that we have different possibilities. The cross can move, put a move here, and it can maximize its value, right? So it means that if there is a move here, it can maximize value, and then it would be a win. However, there are other possibilities. What is the other possibilities? I can put a cross here, although it wasn't necessary if I put a cross here, I would be win. But considering that what are the moves? So I can put a cross here. Putting a cross here will reduce the opportunity for the min function. So it means that the value of the min function is 0 in this case. Although it was supposed to be -1, but we have reduced the opportunity for it to win. Right. Now, if you have put this condition, now the next state is for circle, if you move in the same direction. Next move is for circle. So circle can put a move here, but if it is putting a move here, it is maximizing the opportunity for x. So if it is putting a move here, it is maximizing the max value. However, if could have put move here, it is minimizing the max value, which is the main opportunity. Main function for the min is to minimize, not to maximize. So the best move would be to come to this direction. And then finally, you can see again it is a draw. However, if we say that this certain location was chosen, so you can see if this location was chosen by cross player, clearly we are giving an opportunity to the circle player. So overall, we are not maximizing ourselves, but we are maximizing the minimum player. So that's why you can see that maximizing minimum player means its value would go to -1. And again, if you keep on moving, so now for this has been done for the cross. Now for the circle can put a move here or here. So if circle is putting move here, it is minimizing our chance, but if it is putting directly a move here, it is maximizing its function. So these are different states. Based on minimum and maximum value, we can decide which move we should choose. So this is the overall concept for the min-max algorithm. So if you want to summarize it, in terms of a pseudocode or a function, so we can say that the max player takes an action from the actions list that produces highest value of min value. Highest value of min value means that what is highest value for min? -1 is 0. So it means that indirectly we can say that max value is maximizing itself. And choosing a minimum value, highest minimum value, means that it is minimizing the other function but maximizing itself. And min picks an action from the action list that chooses smallest value of max value. So it means that min is taking the lowest value for max. It means that min is trying to minimize that function, right? And since in this case you can see it was one was in minus and one was in plus, so we can somehow realize it. So you can see here, if you were trying to move to, if it was x position, so what was the function of x? The function of x was to produce highest minimum value. So highest minimum value for min is 0 because itself it's for min function the highest value can be, for itself it can be -1, -2. But from the perspective of max function, the highest value is 0 because he want to push it towards itself so that he can maximize its profit. And same goes here. So it means that min-max function will always work on the value of the move that can maximize or minimize depending on whoever player it is. Okay, so here is that was an example for that game, cross and circle. But this is another example which is, you can say, between two players, a one move game. So it means that each player will take one move and then in the end we'll see that who has the highest value and it will be maximum and that player will win. So this is how we define a two-play game tree. This symbol is denoting max player, one player, and this is denoting the other player. Now, the function of max player is to increase its profit. Consider it as a cricket game. So, the fielding side is trying to take wickets, whereas the batting side is trying to maximize its profit. So, it means that this is the, when we are here, it's the maximizing player move. So, these nodes are basically represented by the maximum value or minimum value. So it means that for player at this location, what can be the best move? Because it is a maximizing player, so it will choose to move towards the node which is maximum value, right? And if you remember, here we said that max player picks highest value of the min value. Of the min value means the next move is for the min, right? So it means that the max will choose a node towards the minimum which gives us the highest number. So it means that when moving from max to min location, we will choose a node which has the highest value. So you can see that here the best move is to go to 3. So it means that we are probably hitting a 6 or doing something to reach a certain point. But now at this point, it is the move for the minimum player. What minimum player is trying to do? It is trying to minimize the other one. So it will try to take to a location which is minimum. So from here, what are different moves? Moves are 12, 8 and 3. But what will the main function will do? Which side will move? It will move to the side which will result in minimum value. So overall you can see that max player tried to maximize his value, but in return min player again did a counter attack. So overall you can see that in this game the game is drawn. But in other words, if max player could have chosen A1 and at here if by mistake the move was B2, so you can see that the final function was 12. So it means that now the overall utility of the overall function is maximized. So it means that the starting and ending point of the max player is higher. So it means that min was unable to oppose the maximum player. So this is another way to visualize these kinds of problems. So here I have written max wants to win, but min want to stop it. Utility is defined as a value of max. So in this problem, we cannot say win or lose like we have done in the previous case. In this case, we can say that who has the highest value. So we have to choose one side. So if, for example, we know that the betting side has highest score, then if we keep on looking the betting side and see if the other side has opposed it or not, then we can decide that whether it is a win or loss. So if we see the value of the utility function for the max, so you can see here the max was 3. In the next state, max could take value 3, 2 or 2. But we know that max will choose 3 value because it is higher. But min, what will min do? Min will try to reduce it. So min will choose 3. So this is how your algorithm would work, and would, based on agent's one move, it will do a counter attack and would try to stop you and would try to reduce your profit. Yeah, so here is another example. So you can see that again, here is the max turn. So what can be the best move here for max? What could be the best move for max? To go to 5, 3 or 9. What is the purpose of max? Purpose of max is to choose the maximum value, right? So in this case, what is the maximum value?
9.
9. So it means that max will try to do a move which gives maximum value to the min function. So it means that you are penalizing the min function by improving yourself. So it means that out of all these, so if you have taken this move, it was 3. If you have taken this move, it was 5. So it means that this move was something that instead of increasing your profit, it was reducing your profit. And when it is reducing profit of 1%, automatically, since this is adversarial search, so it will maximize the other player. Similarly, if you go to this place, so starting is for max. So what would be the best move for max or min? So the start point is minimum. So what would be the best counter attack from minimum in this case? So at this point, the value is 8. So what value should it choose? This is a min starting point, right? It is a time for min to respond. So it is starting from 8. So what could be the best next move? 8 or 9?
8.
8, right? Because if it is not reducing it, it will not allow to increase it. We reached 8. So what is the best possible move from max function now?
8.
8. It will try to go to the highest value. So this is how one is doing an attack and the other one is doing a counter attack. So there is a pseudocode as well. You can go through it. It is the same that how you're going to choose a min value or a max value. The same way I have actually explained that. If you are at this location, you're going to take all these values and then you will see that which one is the maximum value. So if 9 is the maximum value, you will say take the move which brings you to the 9. So this pseudocode explains this thing. So now we're going to go to the lab. I will also give you some feedback on the phase test and then we'll do some tutorial questions.
What?
What's wrong?
I think he means like giving back the paper,
Ah,
so we can see.
Yes, we do.
I don't think
I mean, you don't care, but yeah. I don't know, man. I'm just tired. I just